crash course on large language models. So what are large language models? So the large language models are advanced computer programs which are designed to understand, generate and interpret natural human language. Think of them as incredibly sophisticated language experts who can perform a wide range of tasks, from answering questions and composing a text to translating languages and even composing poetry. Imagine having a personal language assistant who can converse with you in your preferred language, understand your needs, and provide you with accurate information and helpful responses. So, that is the kind of assistant that LLMs can provide. Now, these large language models are built using complex algorithms and are trained on vast amount of text data from various sources such as books, articles, websites, and social media posts. This training allows large language models to learn the patterns, structures, and relationship between the words, phrases, and ideas, which enable them to generate human-like text and understand natural language inputs. So let's discuss some of the examples where LLMs can be used. First is the chatbot. So LLMs are used to create chatbots that can converse with users conversationally and intuitively. And these chatbots can answer questions, provide information, and even offer personalized recommendation. For example, a chatbot which is powered by an LLM can help you find information, troubleshoot issues, or even assist you in shopping online. Then comes the language translation. So these large language models can be used for translating text from one language to another, which makes it easier for people to communicate across linguistic barriers. For example, you can use an LLM powered translation app or a website to translate a text message, web page, or even a book in your preferred language. Suppose you want to translate a book into Hindi from English. So you can do this using the language translation feature of LLM. Then comes the summarization. So these large language models can be used to summarize long pieces of text such as articles, research papers, or news stories into shorter, more concise versions, which makes it easier for reader to digest that information. For example, this LLM powered summarization tool can help you quickly summarize a lengthy article, which saves your time and allows you to focus on main points. Then comes the content generation. So these large language models can be used to generate a wide variety of content such as news articles, social media posts, and even poetry. So this capability can be harnessed to augment human creativity and streamline content creation. For example, this large language model can be used to compose a personalized poem for a special occasion, drawing upon a wide range of poetic styles and structures. Then comes the language learning. So these large language models can be used to create interactive language learning tools which can help learner practice their skills in conversational and engaging way. For example, this LLM powered language learning app can simulate conversations with native speakers, which provides learners with personalized feedback and help them improve their language skills in a fun and interactive way. So these are just an examples of many ways that LLMs are being used to make our lives more convenient, efficient, and connected. As the technology continues to evolve, we can expect to see even more innovative applications of LLMs in future. So today we'll deal about this large language model architectures, which includes transformations, transformers, attention mechanisms, then the training methods or fine-tuning methods, and finally responsible AI principles. So let's start with the attention mechanism. Now this attention mechanism is a critical component of many language model architectures, including transformer based architectures such as BERT, GPT and others. It's a clever way to enable the model to selectively focus on different parts of input when generating a response. Imagine you are having a conversation with a friend. So when they speak, you don't listen to every word simultaneously. Instead, you selectively focus on different parts of what they are saying, depending on the context, to better understand their message and respond appropriately. Right? So this is similar to how LLM uses the attention mechanism. In a large language model, this attention mechanism allows the model to selectively focus on different parts of the input text when gathering a response. So this is particularly important because large language model inputs can be quite long, and the model needs to consider various parts of the input when generating a response. So let's take a simple example to illustrate the attention mechanism. Suppose you are using a language model to generate a summary of news article. Now this article might be quite long with multiple sections and subheadings. So this attention mechanism allows the model to selectively focus on different parts of input text when generating the summary. And it includes the following steps in this. First is the input, which is the entire news article, which may include multiple paragraphs, sections and subheadings. Then comes the encoder. The first step is to encode the input text using an encoder. So this will encode the input into a set of contextualized embeddings, which capture the meaning and relations between the words in the input. And each word in the input is represented by a vector in this set. Then comes the attention mechanism. So this attention mechanism is applied to selectively focus on different parts of the encoded input text, which depends on the context and the task at hand. In the example of generating a summary, the model might pay more attention to the main ideas and key phrases in the article when generating a summary. Then comes the decoder. So this decoder takes this encoded input and the generated summary up to a certain point as input, and then uses the attention mechanism to selectively focus on different parts of encoded input text when generating a next word in the summary. And this process is repeated for each word in the summary. And finally we get the output. So the model generates a summary by iteratively using the attention mechanism to selectively focus on different parts of encoded input text and generate a summary word by word. So to conclude this, we can say this attention mechanism is a powerful tool that enables large language models to generate high quality responses by selectively focusing on different parts of the input text. It is a critical component of transformer-based models and other large language-based architectures, which allows them to effectively process and generate text in a wide range of tasks and applications. So next we discuss what are transformers in LLM architectures. So these transformers are a powerful architecture which is used in large language model. So they were initially designed for machine translation tasks, but have since been adapted to a wide range of natural language processing tasks. So imagine transformers as a sophisticated neural network that can process and generate text in a variety of tasks, much like how a human read and comprehends text. So let's take a simple example to illustrate the use of transformers. Suppose you are using a language model to translate a sentence from English to Spanish. So this transformer architecture will allow the model to effectively process the input and generate a coherent and accurate translation. And it will input the same steps like we discussed just now. First, it will have an input, which is the English sentence you want to translate. Then comes the encoder. So the transformer architecture encodes the input sentence into a set of contextualized embeddings, which capture the meaning and relationship between the words in the sentences. And each word is represented by a vector in the set. Then we have attention mechanism, because we know the transformer was started by attention is all we need. So this transformer architecture uses the attention mechanism to selectively focus on different parts of encoded input text, which depends on the context and the task at hand, which allows the model to effectively process the input sentence and translate it accurately. And finally, we have our output. So the architecture generates a Spanish translation by iteratively using the attention mechanism to selectively focus on different parts of encoded input text and generate a word at a time. And this process continues until a complete accurate translation is generated. Now for doing this, they must have been trained. So the transformer architecture is trained on large amount of bilingual text data such as books, articles and conversation. So during training, the model is presented with various types of inputs and their corresponding translations, which it uses to learn the relations between the words and the patterns that underlie the language. So to summarize this, we can say the transformer architecture is a powerful tool which is used for building large language models that can generate high quality text in a wide range of tasks. Its ability to effectively process and generate text combined with the use of attention mechanism makes it a popular choice for a variety of application, which includes language translation, text summarization and chatbot development. Now let's discuss what are the training methods of these large language models. So when we are training this large language model, means we are exposing them to the wide amount of text data such as books, articles and conversations, and then fine-tuning them to perform specific tasks. And this process allows large language models to learn patterns in language and develop a strong understanding of context, syntax and semantics. But there must be some common training methods which is used to train the LLMs. So first training method is unsupervised pre-training. So this in unsupervised pre-training, this large language model is exposed to a large corpus of unlabeled text data. And the goal is to teach the model to predict the next word in a sentence given the preceding words. And the model learns patterns in languages by iteratively predicting words in the corpus. And it gradually improves its ability to understand context and generate coherent text. For example, a pre-trained transformer based model like BERT or the bidirectional encoder representations from transformer. It's trained on a large corpus of text using unsupervised pre-training, which allows the model to learn general language representations that are useful for variety of NLP tasks. Next comes the supervised fine-tuning. So after pre-training, this large language models can be fine-tuned for specific tasks using label data. So in this supervised fine-tuning means you are training the model on a task-specific data where both inputs and corresponding outputs are known. So which allows the model to learn task-specific patterns and improve its performance on that particular task. For example, we are using a pre-trained transformer model like GPT or the generative pre-trained model transformer, which can be fine-tuned for a specific task such as question answering by training it on a labeled data sets of questions and corresponding answers. So the example of unsupervised was BERT. For the supervised, it was GPT. Okay. That next comes the semi-supervised fine-tuning. Now this semi-supervised fine-tuning is a combination of unsupervised pre-training and supervised fine-tuning. So in this approach, LLM is first trained on large corpus of unlabeled data and then fine-tuned on a smaller labeled data for a specific task. And this approach can be more efficient than purely supervised fine-tuning because the model has already learned a lot from the training process. So in this, the example is the pre-trained models like Roberta or the robustly optimized BERT approach, which can be fine-tuned for a specific task such as text classification using a combination of unsupervised pre-training and a smaller labeled dataset for a specific task. Next comes the transfer learning. So this transfer learning, it involves leveraging the knowledge learned during pre-training to improve the performance on a different task, right? So this approach is based on idea that representations learned during pre-training are useful for variety of NLP tasks. For example, a pre-trained transformer based model like generative pre-trained transformer 2 can be fine-tuned for multiple tasks such as language translation, text summarization, and chatbot development by leveraging the knowledge learned during pre-training. And finally comes the reinforcement learning. So this reinforcement learning means you are training the LLM in an interactive environment where this model receives the feedback in the form of rewards or penalties. And this approach is useful for tasks that requires generating sequence of text such as language translation or chatbot development. For example, a transformer-based LLM can be trained using reinforcement learning to generate coherent and relevant responses in a chatbot. And the model receives reward for generating responses that are accurate, informative, and contextually appropriate. So to summarize this, we can say that these training methods, along with advancements in the transformer-based architectures, have made LLMs powerful tools for a wide variety of natural language processing tasks. And their ability to learn from the large amount of text data and adapt to a specific task has enabled these large language models to generate high quality text and perform a variety of NLP tasks with high accuracy. Now next comes the fine tuning techniques. So here we will discuss the knowledge distillation. So this knowledge distillation is a technique to fine tune a large pre-trained language model by transferring its knowledge transformation. So here the knowledge is transferred to the smaller models. So this technique helps to create smaller and faster models which can achieve similar or better results than the larger models. So to understand this, imagine you have a large encyclopedia which is written by a team of experts and you want to condense that information into a small, more portable guidebook. So this encyclopedia is a large pre-trained large language model and the guidebook is a smaller model. So the knowledge distillation process, it will transfer the expertise and knowledge from the encyclopedia to that guidebook. And this process will involve following steps. First, it will have a teacher model. So here you can choose a large pre-trained large language model which serves as the teacher model. And this model has large number of parameters and is trained on large amount of data. Example, here you can take GPT-3, BERT, Roberta or any language model. Then comes a student model. So here you will create a smaller model which will serve as a student model, and this model will be fine-tuned to mimic the performance of teacher model. Example, you can use smaller version of pre-trained models like GPT-2, BERT small, Roberta base like this. And then we will have some training data. So here you will collect a data set of input-output pairs that the teacher model has been trained on. And this data set will be used to fine-tune the student model. Then we have some soft targets. So the teacher model generates some soft predictions by outputting a probability distribution of a possible answers for a given input. And these soft predictions are used as the target output during the model's training of the student's model training. Then comes the training process. So the student model is fine-tuned using the training data set and soft targets which is generated by teacher model. And the goal is to minimize the difference between the student model prediction and the teacher model soft targets. And this process transfers the knowledge from the teacher model to the student model. And finally, we will have the evaluation of the performance of the student model on the test data set. And here the goal is to achieve similar or better performance compared to teacher model while being significantly smaller in size. So to make the story short, let's take a simple example. So imagine you have a large encyclopedia on cooking and you want to create a smaller portable cookbook. So the encyclopedia is the teacher model, cookbook is the student model. You have collected a data set of recipes from this encyclopedia and then using this encyclopedia's soft prediction, that is probability distributions of our ingredients as the target. Because here we have the targets so that we will check how much accurate our output is. So you'll then fine tune the smaller cookbook model using that training data set and you have the soft targets which is generated by encyclopedia. This cookbook model will learn to replicate that encyclopedia predictions, and in doing so, it will transfer the cooking knowledge from that encyclopedia to the cookbook. And after fine tuning, you evaluate the cookbook's performance by testing it on a set of recipes that it has not seen before. So if the cookbook model can replicate the encyclopedia predictions with similar accuracy, that means it has successfully distilled the cooking knowledge from our teacher model. So normally here just a knowledge transfer is done from a bigger model to the smaller model. Next comes the adapter modules. So these adapter modules are a fine-tuning technique for pre-trained large language models, which allows you to improve the performance of a model on specific tasks without retraining the entire model from scratch. This technique is computationally efficient and enables the reuse of pre-trained models from a wide range of tasks. Imagine you have a large language model that can perform various tasks such as translation, summarization, and language generation. And you want to improve the model performance on a specific task such as sentiment analysis. So here, instead of retraining the entire model from scratch, you can use adapter modules to fine-tune the model for sentiment analysis task. And here the process will involve first the pre-trained model. So here in the pre-trained model, you can use to fine-tune that model using adapter modules. And this model has been trained on a large amount of data and can perform a variety of tasks. Then comes the adapter modules. So you'll create a set of adapter modules which will be added to this pre-trained model. And these modules contain learnable parameters which will be fine-tuned for that specific task. And the number and structure of adapter modules can be tailored to the task at hand. Then you'll have a task-specific data. So you'll collect the data set of examples that are representative of tasks that you want to improve. For example, if you want to improve sentiment analysis, so you'll gather a set of text samples with their corresponding sentiment labels, positive, negative, or neutral. Then we'll have a training process, so where we will fine-tune the adapter modules using the task-specific data. That is, the pre-trained model will remain unchanged, but the adapter modules will learn to transform the input embeddings to better capture the task-specific features. And finally, we will have evaluation, so where we will evaluate the performance of fine-tuned models on a test set of examples from the task. So here the goal is to achieve improved performance compared to the pre-trained models without retraining the entire model. So let's take a simple example to illustrate the use of adapter modules. So suppose you have a pre-trained language model that can perform various text classification tasks such as news article classification, be it politics, sports, entertainment. And you want to improve the model's performance on sentiment analysis. So you can use adapter modules to fine-tune the model for sentiment analysis without retraining it for all text classification tasks. So for this, you will collect a data set of text samples with their corresponding sentiment labels like positive, negative, and neutral. And then you will add adapter modules to that pre-trained model, which can be fine-tuned on the sentiment analysis task. And during fine-tuning, the adapter module will learn to transform that input embeddings to better capture the sentiment of text. And after fine-tuning, you will evaluate the model performance on a test set of sentiment analysis examples. So if the fine-tuned model shows improved performance compared to the pre-trained model, that means it has successfully leveraged adapter modules to enhance its performance on the sentiment analysis task. Next comes the prompt tuning. So this prompt tuning is a fine-tuning technique for pre-trained language models, which allows you to improve the model performance on a specific task by modifying the way you present the task to the model, that is through the prompt. And this technique is computationally efficient and enables the reuse of pre-trained models for a wide range of tasks. So imagine you have a language model that can perform various tasks such as translation, summarization, and language generation. And to improve the model's performance on a specific task such as question answering, you can use prompt tuning by carefully crafting the way you present the task to the model. So here we have taken how do I bake a cake? So it shall give for baking a cake, follow the recipe. So this process of using fine tuning involves the following steps. First, it's same as the previous one. You will have a pre-trained models. So here you can choose a pre-trained LLM that you want to fine tune using prompt tuning. So this model has been trained on a large amount of data and can perform a variety of tasks. Then you will have a task specific prompts. So you will design task specific prompts that will be used to guide the model's responses. And these prompts are carefully crafted to provide the necessary context and structure for the task. These prompts can include instructions, question formats, and response formats that are tailored for the specific task. Then we'll have some task-specific data. That is, we will collect a data set of examples that are a representative of tasks which we want to improve. For example, if we want to improve question answering, so you will gather a set of questions and their corresponding answers. And for doing so, we will have a training process where we will fine-tune the model using that task-specific prompt and the task-specific data. And the pre-trained model will remain unchanged, but its performance on the task will be improved by using the tailored prompts. And finally, we will evaluate the performance of these fine-tuned models on a test set of examples from the task. And the goal is to achieve improved performance compared to the pre-trained models without training the entire model. So let's take a simple example to illustrate the use of prompt tuning. So suppose you have a pre-trained language model that can perform various text generation tasks such as generating summaries or answering questions. And you want to improve the model's performance on a specific task such as generating movie reviews. So you can use prompt tuning by designing task-specific prompts. So here you will collect a data set of movie reviews and their corresponding sentiments, that is either positive or negative. And you'll create two task specific prompts, one for the positive reviews and one for the negative reviews. And this prompt will include instructions and a specific format for generating the reviews. So during fine tuning, you will present the model with a mix of task specific prompts and review examples from the dataset, so that the model learn to generate high quality movie reviews by adapting its response to that tailored prompts. After fine-tuning, you will evaluate the performance of the model on a test set of movie reviews. So if the fine-tuned model shows improved performance compared to the pre-trained model, it has successfully leveraged prompt tuning to enhance its performance on the movie review generation task. Then next comes the parameter efficient fine-tuning. So this is a technique which is used in natural language processing to improve the performance of large language models like GPT-3, BERT and Roberta without having to retrain the entire model from scratch. So imagine you have a car and you want to improve its performance. So instead of completely rebuilding the car, you can make a few tweaks to the existing parts to make it faster, more efficient and more reliable. So here also this parameter efficient fine tuning is like making those tweaks to your pre-trained language model without having to rebuild it. Let's say you have a pre-trained model GPT-3 that is very good at generating human-like text, and you want to use it to answer questions which are related to specific topics such as how to prepare for job interview. So instead of retraining the entire GPT model on that job interview questions, this PEFT will allow you to fine tune only a small portion of model's parameters that are relevant to this new task. So in this example, you can take your pre-trained GPT model and then fine tune it by adding some layers or modify a subset of its parameters to better handle this job interview questions. So this way the model becomes more specialized in answering job related questions without having to retrain the entire model. And this parameter efficient fine tuning is important because it can significantly reduce the computational cost and time which is required to fine tune the large language models for specific tasks. So additionally, it allows you to reuse that knowledge and expertise which is learned by the pre-trained model, which makes it more efficient and cost-effective solution. The next comes the LoRa or the low rank adaptation of LLMs. It is a fine-tuning technique which targets large language models, and it is designed to be computationally efficient and allows the reuse of pre-trained models, which makes it an attractive option for resource constrained environments. So imagine you have a pre-trained language model that can perform various tasks such as translation, summarization, and language generation. Now you want to adapt this model to a new task or domain such as legal document analysis. So to do this, you will use the LoRa technique, which has the following steps. First is the pre-trained model. So here you will choose a pre-trained LLM that you want to adapt using LoRa. So this model has been trained on a large amount of data and can perform a variety of tasks. Then we'll have a task specific data. So here you will collect a data set of examples that are a representative of task or the domain you want to adapt the model to. For example, if you want to adapt the model for legal document analysis, so you will gather a set of legal documents and their corresponding annotations. Then we have model checkpoints. So here we will use the pre-trained model as the starting point and then periodically save these checkpoints of the model during training. And these checkpoints allows you to adapt the model to the new task without retraining the entire model from scratch. Then comes the fine-tuning process. So the fine-tuning this pre-trained model by training it on a task-specific data using that saved checkpoints. So the model will gradually adapt to the new task or the domain while retraining its general knowledge from this pre-training. Then we'll have a LoRa adaptation where we will have low-rank matrix factorization. So during fine-tuning, this LoRa technique specifically target the model's dense weight matrices. And these matrices are factored into 2-rank matrices, which allows for efficient adaptation of model to the new task. Then we have training. So the model is trained on task-specific data using the factorized weight matrices while the general knowledge from the pre-training is preserved. Then we have reassembly. So after training, the factorized matrices are reassembled. And finally, we will evaluate the results on a fine-tuned model or on a test set of examples from the task. And the goal is to achieve improved performance compared to that pre-trained model while retaining the model's general knowledge. So let's take a simple example to illustrate the use of LoRa. Suppose you have a pre-trained model that can perform various text generation tasks and you want to adapt this model to the legal document analysis. So you can use this LoRa by collecting a data set of legal documents and their corresponding annotations such as document type and key information. Then you will use the pre-trained model as a starting point and will periodically save the checkpoints during training. So during fine-tuning, you present the model with legal documents and task-specific data. And this LoRa technique targets the model's dense weight matrices which are factorized and trained on task-specific data while retaining that general knowledge from pre-training. And after fine-tuning, you will evaluate the performance of model on a test set of legal documents and annotations. So if the fine-tuned model shows improved performance compared to the pre-trained model, that means it has successfully adapted to the legal document analysis domain using the LoRa technique. Then comes the CLORA or the quantized low rank adaptation. Well, it's a variant of LoRa or the low rank adaptation of LLM's technique, which is specifically designed for adapting pre-trained large language models while optimizing computational resources and memory usage, which makes this CLORA an attractive option for deployment on resource constrained devices. And the idea behind CLORA is to quantize the pre-trained model parameters to lower precision floating point numbers such as 16-bit floats and use these quantized parameters for fine-tuning, which reduces the computational demands of fine-tuning process while maintaining the model's performance. So imagine you have a pre-trained language model that can perform various tasks such as language translation and language generation. And you want to adapt this model to a new task or the domain such as legal document analysis. So here also we are taking the same example, and but here you have also have a limited computational resources. So you'll use the CLORA technique. And the process will remain same. That is, first you will have a pre-trained model, so which you will choose according to your need. So this model must be trained on a large amount of data and can perform a variety of tasks. Then we'll have a task specific data. So where we will collect a data set of examples that are a representative of task or domain you want to adapt the model to. For example, if you want to adapt the model for legal document analysis, so you would gather a set of legal documents and their corresponding annotations. And then the difference point is the quantization. So here you will quantize the pre-trained model parameters to lower precision floating point numbers such as 16-bit floats or the half precision. So which reduces the computational demands of fine-tuning process while maintaining the model's performance. And then we'll have a model checkpoints, that is, we'll use the pre-trained quantized model as a starting point and will periodically save this checkpoints of the model during training. And these checkpoints allows you to adapt the model to the new task without retraining the entire model from scratch. Then we'll have a fine-tuning process where we will fine-tune the pre-trained quantized model by training it on a task-specific data using that saved checkpoints, which will gradually adapt to the new task while retaining its general knowledge from pre-training. Then we'll have the CLORA adaptation, that is a quantized low rank matrix factorization. So during fine tuning, this CLORA technique specifically target the model's dense weight matrix. And these matrices are factored into lower rank matrices, which allows the efficient adaptation of model to new task. Then we'll have a training, that is model is trained on the task specific data using factorized quantized weight matrices while the general knowledge is preserved. And finally, we will fine-tune the performance on a test data of examples from the task or domain. And the goal is to achieve improved performance compared to the pre-trained quantized model while retraining the model's general knowledge. So let's take a simple example to illustrate the use of CLORA. So suppose you have a pre-trained language model that can perform various text generation tasks and you want to adapt this model to the legal document analysis. But you have limited computational resources. So for that case, you'll use CLORA by collecting a data set of legal documents and their corresponding annotations such as document type and key information. So here you will use the pre-trained quantized model as a starting point and will periodically save the checkpoints during training. So during fine-tuning, you will present the model with the legal documents and the task-specific data. This CLORA technique will target the model's dense weight matrices, which are factorized and trained on task-specific data while retaining the general knowledge from pre-training. So after fine-tuning, you will evaluate the performance of the model on a test set of legal documents and annotations. So if the fine-tuned model shows improved performance compared to the pre-trained model, that means it has successfully adapted to the legal document analysis using this CLORA technique. Now this CLORA is an efficient and effective way to adapt pre-trained large language models to new task or domain while optimizing computational resources and memory usage. So here main difference is the quantization, and we use this when we have the requirement of optimizing the computational resources and memory usage. The next comes the responsible AI principles. So these responsible AI principles are essential for ensuring that large language models are developed and used ethically, transparently, and in a way that benefits society. So let's take some key principles and examples of how they can be applied to the LLMs. So first is the bias and the fairness. So LLMs can unintentionally reflect the bias which is present in the data that they were trained on. So to ensure this fairness and avoid the perpetuating harmful biases, it's essential to identify and mitigate the biases which is used to train LLM. For example, LLM used for job posting should be trained on diverse data set to minimize the impact of gender or racial biases. Then comes the transparency and explainability. So it's important to be transparent about how LLMs work and how decisions are made, which helps to build trust in the model and enables user to better understand its limitation and potential biases. For example, you'll provide explanation for the LLM generated response. It can help user understand why a particular suggestion was made, and it will build the trust in the model's output. Then comes the privacy and data security. So LLMs should be designed and used in a way that protect user privacy and security. And this includes implementing appropriate data protection measures such as encryption, anonymization to safeguard sensitive information. For example, an LLM-powered chatbot should be designed with robust security measures to prevent unauthorized access to users' personal data. Then comes accountability and responsibility. So the developers and users of LLMs should be held accountable for this model's actions and impacts. And this includes taking responsibility for the consequences of model's output and ensuring that it is used ethically and in compliance with the relevant laws and regulations. For example, developers of an LLM powered tool should ensure that the model is not used to generate harmful or misleading content. And they should be transparent about any potential bias which is present in the model. Then comes the inclusivity and accessibility. So the LLM should be designed to be inclusive and accessible to the people with the diverse backgrounds and abilities, which includes making the model accessible to people with disabilities, such as those who use screen readers, and ensure that the language used is inclusive and respectful. For example, the LLM which is used for generating content should be trained on diverse dataset that include a range of languages, dialects and accents to ensure that a model can effectively serve our diverse user base. Then we will have a continuous evaluation and improvement. So it's important to continuously evaluate LLMs to ensure that they're performing as intended and to identify and address the unintended consequences. So for example, LLM used in healthcare setting should be regularly evaluated to ensure that it provides accurate and helpful responses, and any biases or inaccuracies should be addressed through updates and improvements. Then we have some ethical considerations. So the LLM should be developed and used in a way that align with the ethical principles such as the respect for human dignity and privacy. So for example, an LLM used for content generation should be designed to respect intellectual property rights, such as avoiding plagiarism or generating content that violates copyright laws. So these responsible AI principles are essential for ensuring that LLMs are developed and used ethically and in a way that benefits society. So by prioritizing transparency, accountability and inclusivity, LLMs can be leveraged to drive innovations and positive changes while maintaining the risk associated with their use. Thank you.